I'm Troy McClure. You perhaps have seen me in such fine quality chemistry videos as "My lab coat's on fire, what do I do now?" or "Isn't it ironic that it's ionic?" Today we're going to be looking at orbitals and covalent bonding, okay? And for that, we've talked about orbitals in the past. Think of them as regions, areas where the electrons hang out and they bounce around. And you may notice here, for example, this would be the nucleus of the atom here, and you'd have a 1s and a 2s and a 2p. And if you kind of notice how the arrows go here, that has to do with the electrons spinning in opposite directions. Now when they're inside a sublevel like this, they're bouncing all over the place. So really, when you think about it, the atom is mostly empty space, which is a very fascinating thing. But that's all great and dandy. Well, what happens when we end up getting two of these together? Well, what's going on? What's going to happen with these orbitals, these regional orbitals? Well, here's the thing. The orbitals themselves are not going to explain away the molecular geometry. They're not. Okay? It's just not going to happen. There's got to be something else. Now, in the past, we have done different versions of molecules. We've looked at the methane, the simple drawing, think Lewis dot structure. Here is methane again with the shape, the pyramid shape or the tetrahedral shape. It's a ball and stick model. And then here is the space-filling model of methane, again, CH4. And of course, the question comes down to, notice that the models, that's what they are. They're models, okay? And it's the best way that chemists, scientists, if you will, try to explain what does the atom look like, okay? So let's move on a little further. Now, keep in mind, we're looking at the valence electrons for carbon. We're going to use carbon. Now, carbon happens to have 6 electrons. Now, 2 will go into the 1s orbital, okay? Level 1, sublevel s, the 1s orbital. Then we have 4 more left. 6 take away 2 gives us 4. So that means we're going to have 2 in the 2s, and we're going to have 2 in the p. So the idea is that if we were to go and combine these s and p orbitals, what's happening? Well, in theory, okay, the p orbitals themselves would be at right angles. But the problem is, they're not. Something's happening. What is this? What we expected and what we actually found were 2 separate things. And that means that there's got to be some kind of a change that's happening. And this is when we talk about the localized electron model, okay? Where we focus basically on the electrons in that immediate area. And that's where we get into hybridization. Hybridization is when we have a combination of something. For example, in real life, a lion mating with a tiger, you get a liger. They actually do exist. Feel free to look that up on Google with the image, L-I-G-E-R. Okay, that's a hybrid. Okay, now here in hybridization, we're looking at, we can take the s and the p orbitals of these valence electrons and we can blend them in such a way that it would actually explain the tetrahedral geometry that we are seeing. So we can combine one s orbital and the 3p orbitals. So we have an sp3 hybridization. And that would explain the tetrahedral geometry that we would be seeing here. And that's what we're seeing here if we take the 2s, the 2p in the x direction, the 2p in the y direction, and the 2p in the z direction. Okay? Imagine taking those and combining them into one. That's the hybridization. And you can see the picture here. So what you have, instead of having these p orbitals that look something like this, we have an sp3 orbital that looks like this. Okay, it looks very kind of weird, but this is what the carbon in the center, and you have all these sp3 orbitals around the hybridized orbitals, and then we've got our hydrogens that are attached. Whoa, wait, what do you mean, how? What's going on? Well, the idea is this. The localized electron model explains that we can take a 2s, 2p in the x, 2p in the y, 2p in the z, and we can actually hybridize them. okay? And the idea is, it's not we that's hybridizing, it's naturally happening. It's happening on a natural basis. So when we look at it, if we combine these, what we're going to get, these four pieces, combine them together, and we got these four pieces together, and it looks a little bit weird. They kind of look like mushrooms at a weird angle. Well, especially like these. These look like mushrooms. Well, this one looks like a mushroom the most. Okay? Well, what happens? Well, they combine. They combine, and that's where you get this weird looking thing. Okay, this weird looking hybrid. Okay, so what about molecular orbitals? Okay, we're still kicking around the idea of the localized electron model. Now, the idea is this, that there is an overlap of the atomic orbitals from the separate atoms. Okay, remember now, the idea is we're taking two atoms, and we're going to use two carbons here. If we're combining them together like this, there's going to be some blending. There's going to be some blending with these atomic orbitals. And the idea is when you have an overlap of these atomic orbitals from the separate atoms, that's what we call the molecular orbitals. Now, each molecular orbital would have 2 electrons in the process. Now, there's only 2 types of molecular orbitals. There are sigma bonds and there are pi bonds. Now, the sigma bonds, right here, you can see how the orbitals combine together, and you notice where there's an overlap right here. This is a sigma bond right here. The pi bonds themselves, if you notice, it is dealing with the p orbital, but it is the connection that the electrons are able to hang out in this area, and they call them the pi bonds. Now, the sigma bonds are between the atoms themselves. In other words, they directly connect to each other. With the 2 atoms, they actually connect to each other. The pi bonds, on the other hand, if you look at this as a pi bond, this is a pi bond, they're not directly connecting to another atom. Not really. But the sigma bonds are, and that's a key thing to pay attention to. All right, so let's look at this idea. For sigma bonding orbitals, now we can take s orbitals on separate atoms. And we know our beloved s orbitals because it's a nice, cute little sphere. And imagine when we combine them together, there's going to be an overlap. Well, that's the overlap. That's what the overlap looks like. It's the sigma bonding molecular orbital. That's the hybridization. That is part of the hybridization that takes place there. So, what would that look like for sigma bonding orbitals? If we were taking p orbitals on separate atoms, where this is atom number 1, there's the nucleus of atom number 1, there's the nucleus of atom number 2, and if you were to combine them, you end up having a sigma bonding molecular orbital. That's the general idea, okay, that there is a blending, there is a hybridizing that's there. So that's the sigma. Now, what about pi bonding orbitals? Well, this has to do with p orbitals on separate atoms. So here's an example. We got 2 atoms here. Here's the nucleus of one. Here's the nucleus of another. Okay, now imagine if we can combine them together like this. Now the sigma bonds would run underneath here. They would run in between the atoms. But look what happens with the pi bonding. Instead of becoming separate things like this, like fingers, now it's like taking fingers and you're putting a piece of tape across it, and what makes this special is now the electron would bounce around in here, now the electron can bounce up here. The electron now has much, much more room to bounce around, okay? And this is pi bonding. This is what a molecular orbital for pi bonding would look like, because the center is here. This is where you have your atoms that are connected together. Okay, so on the one hand, when you look at the sigma orbital, here's for 2 of them, okay, we can look at the sigma, how that is bonding, and notice here for the nuclei of the atoms, you got a lot of playroom here for the electrons to move around, and they can go around and they can do that, okay. And then when we look at pi bonding, the action is happening on the top and the bottom, but not directly on the atoms themselves. So that's a key thing there. So, What more about sigma and pi bonds? Well, first thing to pay attention to is that all the single bonds are sigma bonds. All the sigma bonds are in fact single bonds. Okay? A double bond is one sigma and one pi bond. And a triple bond is one sigma and two pi bonds. This is a very important idea. Very, very important, because we can look at something like this here, where we have two carbon atoms triple bonded. Well, what would a triple bond contain? Well, it's going to contain a sigma bond, okay, and two pi bonds. Well, let's take a look at this for a moment. So let's look here for a moment. All right, you have a triple bond, so your sigma bond is here, and you have one pi bond here, one pi bond here. So wait a minute, what's going on? Where's this hybridization, this sp thing? Well, for the pi bonds, if you notice, when they join, when they come close, they form that molecular orbital. Okay, and then when we're looking at here, for the sigma bond, it's an sp hybridization that they have there. Okay. Now this is looking at two carbons. We're looking here at two carbons for that. All right, what does that mean in terms of energy? Well, if you're thinking about taking the 2s and combining it with the 2p, notice you got one sublevel on the 2s, we expect that. We got three sublevels on the 2p, 2p in the x, 2p in the y, and 2p in the z direction. So when they hybridize to an sp3, there's the s and there's your three p's, so it's an sp3. Check out the energy level. The energy level is actually lower. It's in between the 2s and the 2p. Okay? Well, what does that mean? Well, the energy level is less than, the hybridization is actually less than the 2p energy, but more than the 2s. What does this mean? Okay? If it's at a lower energy for the hybridization, that means more stability for the atom. Because remember, when you're forming a bond, the key thing is for the energy, you have to have lower energy level, because that promotes stability. Because if you have more energy in there, that means the electrons are going to be a little bit, they're going to have more energy, and then they're going to be less stable. So you're going to see things fall apart, but we're not seeing this. Now, how is it that we get to this hybridization? Well, we know the geometry from the experiment. We know the orbitals of the atom, okay? And hybridizing atomic orbitals can explain the geometry. So if the geometry needs a tetrahedral shape, it is an sp3 hybridized. Now that does include bent and trigonal pyramidal molecules, because one of the sp3 lobes actually will hold the lone pair for this, okay? So localized electron model, the sp2 hybridization, again, same concept for the C2H4. All right, so here we have the sp2. So here's our s, here's p in the x direction, p in the y direction, and then when they combine, they form the three parts. But remember, don't think of these as separate, independent individuals, because they combine as one. That's the hybridization. That's the hybridization that they're talking about. So, moving on here, so we've got this happening. So we got, and, bam, we have an sp2 hybridization. So that's what it would look like. I showed you the three pieces. Now, let's check this out. In terms of energy, look at that sp2. Remember we did the sp3 just a moment ago. So we have 2s and we have 2p. We have our three regular sublevels in 2p. But we're only using two of those p's. So we have an sp2 hybridization right here. Well, where's that third p? Oh, it's going to be up here, normally. But check out the energy. The energy is lower compared to the 2p. And that means if it's lower energy, more stability. That's a big key. That's a pretty big key. So where is this pz orbital? It's the perpendicular. And it is the overlaps of these orbitals that make the sigma bond. okay, that make the sigma bond. And when you look at it here, look at these two carbons here, C2H4, okay, right here, that's where it is. That's where your sigma bond is. Before that, we talked about two types of bonds, sigma bonds and pi bonds. Sigma bonds are forming from the overlap of orbitals. Now the orbitals themselves, they can be s or they can be p, okay, for our purposes here. But the sigma bonds are also between the atoms, and that's the key thing you need to understand, that the sigma bonds are the only ones that happen between the atoms. It can be an S, it can be a P, or it can be a hybridization. But the bottom line is, for the SP, for the sigma bonds here, 2 electrons, and that's directly in between the atoms, where if we look at the pi bonds, okay, remember, they can overlap. But they overlap, but they are not connected directly to the carbon. Not like here, okay? So that's part of the story, okay? So pi bonds are above and below the atoms. They are adjacent, between adjacent p orbitals, the two bonds of a double bond, okay? That's the two bonds of a double bond. So when we look at a double bond here, double bond is 1 sigma, 1 pi. Here's your sigma, here's your pi. This is a double bond for this carbon. If it's triple, it's going to be the sigma bond and the 2 pi bonds here as well. Okay, so here we have our molecule, and now you guys can see, here's the sp2 hybridization right here, and you notice that it forms its sigma bond. Great. We have our 1 pi bond here, we have another pi bond here as well. So just letting you guys know, I'm going to fly through sp2 hybridization. We already went through that. Okay, what about electron pairs? Okay, it gets to be linear, like this. All right, localized electron model, sp hybridization. Again, look at that. It just really, it's a mind blower with what these guys will do. And again, in terms of energy, look at your sp. All right, look at your sp hybridization. Notice you're not dealing with hybridization at 1s. You're not dealing with that. Okay, CO2 can make 2 sigma and 2 pi bonds. The oxygen can make 1 sigma and 1 pi bond. So this is what carbon dioxide would look like in terms of. So you've got sigma bond here, here, but you also have a pi bond. Now it doesn't matter if it's here or here for the other electrons. Okay? So I'm just letting you guys know. So here for N2, same idea, that hybridization that's there. Okay, so if you got 2 ends together, it tends to be, oh my, a triple bond. Okay, let's keep going because I'm running out of time here. But I wanted to show you guys a little bit about breaking the octet. At this point, I am going to stop here because we were really focusing on the hybridization, which you guys got to see when we talk about sp2, sp3, or sp. Okay, we know that the orbitals themselves, when you combine 2 atoms together with their orbitals, the orbitals hybridize. And there's going to be overlapping, and then you're going to see the formation of sigma bonds between 2 atoms, and then the pi bonds, which are above and below the atom. Hey, I hope this helped you guys out, and I'll catch you all the next time. Take care.